Hello everyone, my name is Sharaf and today I'll be telling you how we can use meta-learning to learn an active learning policy under fairness parity constraints. This is joint work with Daumé and Renkun from Microsoft Research and the University of Maryland. The main research question we try to answer in this work is how can we use meta-learning to learn an active learning policy under a constraint on fairness parity. Let me start by setting up the stage for the definition for the parity constrained active learning setting that we study in this work. You are probably familiar with the standard active learning setting, where in this setting the learner is presented with a pool of unlabeled training data, and our goal is to learn an active learning policy pi that will generate a categorical probability distribution over the pool of unlabeled data U. Having generated this probability distribution, we sample B points to query for the label for, and then we train a downstream classifier by running a learning algorithm A on the B labeled samples. And you can think of the learning algorithm A as a learning algorithm by backpropagation. In contrast to the standard active learning setting, we are not only interested in improving the accuracy of the classifier, but we are also interested in making sure that the model is fair with respect to different demographic groups. So we evaluate the model on both the accuracy as well as a metric that measures fairness parity, something like demographic disparity or equalized odds. So our goal is to manage an efficacy versus annotation cost trade-off under a target parity constraint measurement. And the way we go about solving this problem is using a meta-learning technique, where at training time we assume access to a fully labeled dataset that could be possibly biased, and then using this labeled dataset, we simulate a parity-constrained active learning setting as I described before. Crucially, we keep track of the full computational graph generated by the learning algorithm, and to ensure that the approach is end-to-end differentiable, we use a Gumbel softmax trick to sample from the discrete probability distribution generated by pi. We formulate the parity-constrained active learning task as a bi-level optimization problem, and we solve this optimization problem using forward-backward splitting optimization approach that makes sure that we satisfy the fairness parity constraint. We compare our proposed approach against alternative strategies for active learning, where here we evaluate the performance against alternative algorithms. The x-axis represents the learning budget, and the y-axis represents the for the figure on the left represents the F-score, and for the figure on the right represents the demographic disparity. And our approach outperforms alternative strategies in this setting. These are some more results where we show the trade-off between the demographic disparity and the F-score for the figure on the left, and the error rate balance and the F-score for the figure on the right. And our approach is the only approach that maintains high F-score while abiding by the small demographic disparity and error rate balance trade-off or constraint. So in conclusion, we presented an approach for using meta-learning for solving the fairness parity constrained active learning task. And we formulate this problem as a bi-level constrained objective function, and we solve it using the forward-backward splitting approach. So thank you so much, and I'll be happy to take questions in the Q&A session.